Good morning, everyone. It's my great pleasure to be here, and I wanted to very much thank the organizers for the opportunity to come and speak. So I'm going to be speaking today about work that we're doing at Penn State University in collaboration with a large team of people, including collaborators from IBM Corporation, as well as from the University of Connecticut and the Smithsonian Astrophysical Observatory. So piezoelectric materials fundamentally are utilized to convert between electrical and mechanical energies in solids. And because they do this conversion, they can be utilized in a wide variety of applications. And what I'm going to try and talk through is some of the fundamentals of how one chooses materials for these applications, as well as some work on utilizing microelectromechanical systems for energy harvesters, for adjustable optics, and potentially for replacements for the silicon transistor. And so I'm going to organize the talk by beginning to discuss the crystal structures of the materials involved. So the very highest piezoelectric coefficients that are available in solid materials all appear in the perovskite crystal structure. We'll do it like this. And in the perovskite crystal structure, we have large ions like lead or bariums that sit at the corners of a unit cell, a titanium or zirconium that sits close to the center of the unit cell, and oxygen atoms that sit at the centers of the faces of the unit cell. At elevated temperatures, this is a centrosymmetric crystal structure so that the center of positive charge and the center of negative charge are physically co-located, with the net result that these materials have no polarization and no piezoelectric response. But at finite temperatures, typically below around 350 degrees in the case of lead zirconate titanate, the atom that should be at the center of the unit cell displaces from the center of the unit cell. And as it does so, the center of positive charge shifts up in the center of the unit cell with respect to the center of negative charge, and we produce a spontaneous polarization. And as the material develops this polarization, it elongates parallel to the polarization and contracts laterally. And that points out that these materials have a strong coupling between polarization, which is an electrical signal, and shape, which is the mechanical signal. So fundamentally, this will be the origin of the piezoelectric coefficient in these materials. To maximize the response, we tend to poise materials at the brink of a structural instability, and I'm going to show the case for the tetragonally distorted material where this atom displaces towards one of the adjacent oxygens, and the rhombohedrally distorted material where it displaces close towards three of the adjacent oxygens towards one of the cube corners. And that is the value of that is shown here. Here is the phase diagram for lead zirconate and lead titanate. Below this line, which denotes the Curie temperatures of the solid, the material has a ferroelectric distortion. On this side, the material is tetragonally distorted. Over here, it's rhombohedrally distorted. And we have a nearly temperature-independent phase boundary between those two. At that temperature-independent phase boundary, we have a significant maxima, and all of the coefficients that depend on polarizability, including the piezoelectric responses. And so if we look at these materials and try and imagine why do they show this electromechanical coupling, I've shown the two primary mechanisms here. The first is what I will call the intrinsic response, where you can see as we apply an electric field that's parallel to the polarization direction, we displace that atom that should have been at the center of the unit cell progressively further off the unit cell, and as it does so, the unit cell continues to elongate parallel to the polarization direction, and it contracts laterally. There's a second major contribution associated with the fact that these materials are all ferroelectric, so that they have more than one possible orientation for the polarization. So I show here the case where I have polarization in the up direction and polarization directed off to the left. And you can see that those two ferroelectric domains have different shapes, different distortions. And as I move the domain wall, that's shown in green, past the solid, through the solid, there is an accompanying shape change that's associated with that as well. And those two mechanisms are the primary mechanisms by which we develop functional, large piezoelectric responses in materials. Although I showed in the schematic the domain wall moving in a very uniform fashion, in reality this is a planar defect. It is moving through a solid which is in itself defective, and the net result is that I have to move these planar defects past the defects in solids which act to pin them. And the net result is that if I look at the potential energy as a function of position in the solid, I will end up moving domain walls from a deep potential well where I can excite it from the bottom of the well with an electric field, but when I pull the electric field off, it will tend to recover to its original position, so that I will have a reversible contribution to the piezoelectric response associated with the motion of the domain walls. But if I can actually move a domain wall from one potential well to the next potential well, the net result will be that I will develop irreversibility in the response. Larger responses, but irreversible responses. And we often will utilize choices between the relative magnitudes of the intrinsic and extrinsic responses to optimize materials for particular applications. So let me try and justify that here. All of you are carrying around piezoelectric thin films for microelectromechanical systems. They are the frequency filters that are used in your cell phones, that are used to distinguish between the transmit and receive portions of the circuit. I think most of you will appreciate that if you were to compare the cell phone of today to the cell phone of 10 years ago, which was a nice brick, quite heavy, didn't speak on as many frequency bands, and one of the main reasons that those phones were literally larger is that they used a dielectric resonator that was roughly the size of my finger to do that frequency filtering. Out of a nice high-density ceramic, you need at least one of those for every frequency band on which you're going to operate. And so modern cell phones have at least 6 frequency bands in them. There was a tremendous incentive to reduce the size and weight of that component. And the approach that was taken was to utilize an aluminum nitride thin film. Aluminum nitride thin films are piezoelectric, and as I apply an electric field in the thickness, I will generate an oscillation that corresponds to the frequency of the cellular communications. And there is an electrical signature of that mechanical oscillation. These are materials that couple between mechanical and electrical energies. That electrical signal and the change in the electrical impedance is what's used for the frequency filtering. And the main advantage is that that is the size of a current generation thin film bulk acoustic resonator. It's on the order of a millimeter in scale and 0.5 millimeter in thickness, and this you can literally afford to carry around in your pocket. If we look at the materials choices for this application, the key material to date is aluminum nitride. That's because the important figure of merit for this application is the electromechanical coupling coefficient, K squared, times the mechanical quality factor. The larger the mechanical quality factor, the more times it will oscillate before that oscillation is damped. So if I want a material that's going to have very low power, I want very large mechanical cues in the material. And if you look at the available materials for this application, aluminum nitride is still the champion. Even though it has very, very modest piezoelectric coefficients, we would be very much interested in replacing this material with a ferroelectric solid because the coupling coefficients are much larger, they can make much broader bandwidth devices, but at present we still pay a penalty in the mechanical quality factor because domain wall motion is dissipative. We lower the mechanical quality factor and hence lower the figure of merit. So for the cell phone application, non-ferroelectric materials like aluminum nitride win. But because their piezoelectric coefficients are really quite modest, there are numerous applications where they are not so successful. And let me try and motivate that on this slide. There is considerable interest in being able to make sensitive sensors or accelerometers. I show here an accelerometer on a fingertip. This is about 7 millimeters on a side, had about 7 microns of a lead zirconate titanate film on the back side of this silicon wafer. And you can see the silicon wafer has been machined using deep reactive ion etching to make a thinned area. Now, if I undergo an acceleration in this direction, the thinned area flexes, and as it flexes, it bends the piezoelectric material, which puts a stress on it, and hence I can make a very, very sensitive measure of acceleration. We were building this sensor to work with a company that was very interested in being able to do condition-based maintenance. In particular, for rotating industrial equipment, they were interested in being able to monitor the bearings in a paper mill. 20 years ago, if you seized a bearing in a paper mill, it cost about $1 million to repair. And so they periodically would have to turn the tool off and sort of at a guessed timetable for when the tool was, perhaps in danger to do preventive maintenance. And what they were really interested in being able to accomplish was to be able to place a sensor that could radio out intermittently. I'm okay, I'm starting to pick up the jitter that's a characteristic of a premature failure. Turn the tool off and do the maintenance. So we built a really sensitive accelerometer. The company we were working with built the application-specific integrated circuit and did all the frequency filtering and had the wireless communications package so that they could literally do the long-distance transmit to a centralized facility. The overall device package was about this size by about this dimension, and about 90% of the volume of that device was batteries to run the device for 6 months for a period of 6 months to 2 years. And I ask you to stop and think about this. One does not need a measurement of vibration every second. Probably every couple hours, or maybe even once a day would be adequate. And the rest of the time, you have a material that converts between mechanical and electrical energy sitting on a piece of rotating industrial equipment. And so the clever thing to do is to actually utilize the material in reverse the rest of the time to convert between mechanical and electrical energy and dump that energy back into a battery so that you can utilize that device for much longer time periods. So here is a piezoelectric film that's on one of my students' fingers. You can see every time he flexes his fingers, he's able to generate a power output. So the same basic approach will work for a number of in-place sensors, and I ask you to think through the logic of this for applications like the Internet of Things. So if we consider the Internet of Things, and if we decide that we're really going to go ahead and do this, and we place 1 trillion sensors, we either need to run wires to 1 trillion sensors, or we need to figure out how to locally power 1 trillion sensors, or we replace 500 billion batteries on an annual basis. And that just sounds like a dreadful job, so it would be very attractive to be able to do some local powering, and everything vibrates. So this is one of many potential modalities to be able to enable the Internet of Things. The key figure of merit for the sensor application is the piezoelectric E31 coefficient divided by the permittivity. For energy harvesting, the key figure of merit is that piezoelectric coefficient, the charge coefficient times the voltage coefficient. And I'll come back and talk about actuators in a moment. But let's think first about this mechanical energy harvesting application. So for the most part, most ambient mechanical energy is available below about 100 hertz. And if I'm going to make a microelectromechanical system, it's inherently small. This is what the micro implies. So how do I make a small object vibrate at low frequencies? I make it very small, thin, and I hang a heavy weight from the end of it. Okay, so typically we will make end-loaded cantilevers. If you look at the power that is available out of an end-loaded cantilever, there's one set of terms that really depends on the geometry of the cantilever, but the key materials figure of merit is the piezoelectric E31 coefficient divided by the relative permittivity. So that coefficient squared divided by the relative permittivity, that is my figure of merit for this application. And if you look at the literature to say, well, what should we choose? You can take a wonderful piezoelectric material like lead zirconate titanate, which has a very large piezoelectric coefficient and a large dielectric constant. It has a figure of merit of about 0.12 coulombs squared per meter to the fourth. Or you could take a material like aluminum nitride, which has a terrible piezoelectric coefficient and a really small dielectric constant, and you get the same figure of merit, and that's just depressing. And so we had a bit of a look at, can we actually do better in a lead zirconate titanate film? And our approach here was to recognize that all piezoelectric materials are inherently anisotropic, which means that the dielectric and the piezoelectric coefficients are a function of the direction in which they are measured in these solids. And if I take a 100 oriented lead zirconate titanate material with the polarization direction out of plane, that gives me the smallest dielectric constant and the largest piezoelectric coefficient. So this is the ideal situation for an energy harvester. If you calculate what you should get for an energy harvesting figure of merit, that moves you from this 0.1 coulombs squared per meter to the fourth up an order of magnitude. Order of magnitude is worth chasing, so we decided to find out whether we could in fact experimentally achieve this predicted value. And the approach that we took, since you need relatively large volumes of piezoelectric, we can't use epitaxial strain here, is to utilize thermal expansion to generate the strains that we need. If you grow a thin film on a substrate with a small thermal expansion coefficient, then we put the film in tensile stress. Remember that the material's elongated to parallel to the polarization, so when I put the material in tensile stress, I tend to fold the polarization into the plane. This is what you get when you grow those films on silicon, and it's absolutely the worst scenario for an energy harvesting application. So the largest dielectric constant, the smallest piezoelectric coefficients. What we really want is to put the polarization out of the plane of the film by compressing it, by growing it on a substrate with a larger thermal expansion coefficient. So working with the group of Professor Hiroshi Funakubo of Tokyo Institute of Technology, one of my students grew lead zirconate titanate films from a actually quite wide variety of compositions, and here's the amount of polarization we get out of plane, and here's the figure of merit, and experimentally you actually achieve that full order of magnitude improvement in the figure of merit. Very interesting. Let's go build a mechanical energy harvester out of this. So the substrates we utilized for this application were substrates like calcium fluoride or magnesium oxide or strontium titanate, nice ionically bonded solids which are inherently brittle. And we need to make a functional energy harvester, make something that's very thin and hang a heavy weight on it. So we now need to machine this brittle material. And it turns out that absolutely everything that etches those substrates also etches lead zirconate titanate. So we made wonderful films, and we destroyed actually several generations of wonderful films, trying to turn them into functional harvesters. So we developed a very elaborate protection scheme for the front and the back side of those devices. We finally got some of them to survive. And now we make a thin structure out of a brittle material, hang a heavy weight on the end, and shake it. And hallelujah, crack propagation happens. And so our devices work once, and then a crack runs through the root of the cantilever and destroys the device. Well, this was very depressing, so we decided we were tired of this, and we thought perhaps we should work on a material that's inherently more mechanically robust. And metals, of course, are really quite mechanically robust. They will deform plastically as needed, so we learned how to do, they also have larger thermal expansion coefficients than lead zirconate titanate, so they offer the opportunity to be able to make machinable microelectromechanical systems as energy harvesters with good figure of merit, to be able to grow the lead zirconate titanate films on these devices. We passivate with a layer of atomic layer deposited hafnium oxide. We put down an orienting bottom electrode. This is an oxide electrode, lanthanum nickelate, and then we can grow either by chemical solution deposition or sputtering a very high strain, high figure of merit piezoelectric material on that device. And here shows an example of operation of one of those energy harvesters. So you see a shaker table behind that we're literally shaking our device. Here is our cantilever with the heavy weight on the end, and this device is mechanically really robust. You can shake it very hard, and it behaves very nicely. You will also notice that it's not a conventional cantilever. You actually see hinges here, here, and here. The mechanical design was suggested by one of my colleagues, Professor Chris Rahn, and has the advantage of far more uniformly straining the piezoelectric layer. So in a conventional cantilever, this area is strained fairly well when you bend the cantilever. This area is largely along to control the resonance frequency, but it's not very functional from the standpoint of making a harvester. What you really want to do is to be able to bend that harvester into a perfect parabola. And now I can strain uniformly the entire volume of the piezoelectric material. Here we put piezoelectric both on the front and the back surfaces, and these hinges allow us to get close to a perfect parabola. We were able to make devices with nice low resonance frequencies. We predicted 5 hertz, we got 6 hertz. The difference is largely due to a finite stiffness on that hinge. And this shows a comparison of this work to other work in the literature. So everybody makes devices with different resonance frequencies, they shake them different amounts, and so you really need to normalize all those results. I'm going to ask you to concentrate on this last column here, and you can see that when you use a material which is designed to be a very good mechanical harvester, it's designed to have a high figure of merit by control of the domain state, and you put it into a structure that utilizes that strain effectively, you can do about 50 times better than anything that has previously been reported. And this is large enough for most self-powered wireless sensors using ambient mechanical energy. If we imagine moving forward and trying to think about, well, can we actually use the motion of the human body to prepare sensors that might be used, for example, to correlate between personal environmental exposure and personal health outcomes, be really nice, for example, to be able to do real-time measurements of ozone concentrations. Ozone is a known trigger for asthma, it's a known trigger for cardiac arrest, and the human nose is a very poor sensor for ozone, which means that people often put themselves at risk by walking into an environment that literally has either high particulate concentrations or high ozone concentrations, and they may then have trouble, usually about 24 hours later, with an asthma attack. And so it would be really interesting to imagine, can I put something on a wrist that powers the environmental monitor so that I don't have to change batteries on those devices all the time. This would replace an environmental monitor that's roughly this size. They make kids carry that around in backpacks in the US, not very appealing. Really like to make something that would be just easier to utilize. And so we've been looking at actually taking mechanical harvesters. This one was actually intended for a wrist platform. And you can see that in this particular device, we have a series of pedal-shaped piezoelectric cantilevers with magnets on the end. And we have an eccentric rotor that as you actually move your wrist or swing your arm while you're walking, it runs magnets in the eccentric rotor past the magnets on the piezoelectric, and it magnetically plucks the piezoelectric device. And you can see this is a swing arm. We built a mechanical arm since everybody is a little bit different in terms of the way that they walk, and we wanted to be able to estimate how much power we could get out for different people. We think we can get about 42 microwatts using a walking motion. To increase that further, we actually need to flip the cantilevers from this configuration where they're oscillating like this to this configuration where they literally have more room to oscillate. And so we're now in the process of building an in-plane plucked harvester. Here you can see the eccentric rotor. That's what moves as we move, tries to swing in response to gravity. If we embed magnets in that, we can use those magnets to pluck the piezoelectric elements. And we think that this device, for realistic achievable values of the piezoelectric coefficient, should give us about 3 times more power during a conventional walking motion relative to the out-of-plane devices. And you can see the operation of our very first prototype here. You're looking at the end of one of those cantilevers with a magnet on it, and you can see that as the magnets from the eccentric rotor run past it, you start this cantilever oscillating, and we use that oscillation in order to generate mechanical energy, electrical energy. So that gives you sort of a flavor of how piezoelectrics might be potentially interesting for energy harvesting applications. I'd like to move to something really quite different, which is how potentially piezoelectric microelectromechanical systems may help us explore the origins of the universe. We've been working with a group at the Smithsonian Astrophysical Observatory on the replacement for the Chandra X-ray Space Telescope. The Chandra telescope is the current state of the art. One focuses X-rays on reflection, which means that I need to have a hyperboloid-shaped mirror segment, and it has to have a very, very precise geometry. In the Chandra telescope, they flew sheets of glass that were about 1 centimeter in thickness, and they were quite large. To fly 4 of those reflective surfaces, it was 800 kilograms of glass. And it was that much glass literally because they needed it to be so stiff that it would not deform when you launched it into space or on gravity release. The problem is with only 4 reflecting surfaces, you are limited in terms of the brightness of the objects that you can detect. And so the Smithsonian Astrophysical Observatory said, if we're going to launch, it's been variously called SMART-X or the X-ray Surveyor or the Lynx telescope, we really want more reflective surfaces, which means the glass has to be thin. And now we need to be able to correct its geometry if it's incorrect. So can you please put a piezoelectric layer on the back side of the mirror surface so that when we apply an electric field, we can actually change the shape of that? And they want to fly a lot of this adjustable optic. Depending on which version of the telescope actually flies, it'll probably be somewhere between 200 and 10,000 square meters of adjustable optic. That is a lot of microelectromechanical system. So we're having a bit of a go at this, and so we learned how to do the deposition of these thin films on glass. What I'm showing here is actually wavefront measurements. So we're looking at the distortion of the glass surface that we can generate when we progressively actuate 3 elements on a adjustable optic. And you can see that we can reproducibly control the surface figure. The amount of deflection that can be generated is adequate to correct all of the projected errors in the optics for the next generation telescope. And so they would like to have individual piezoelectric adjusters roughly every 5 millimeters on a side for 200 to 10,000 square meters of adjustable optic. And the way they currently do the connections for that is there's this one woman at the Smithsonian Astrophysical Observatory who glues wires one at a time to each one of those elements. That sounds like another dreadful job. I don't want that job, so let's figure out if we can be smarter about this. And certainly, we all carry devices that use much more efficient approaches to being able to generate large numbers of contacts by doing row-column addressing. If you can do row-column addressing, then even for a 40 by 40 array, you can drop from 1,601 contacts to 81 contacts. They're now all out the sides of the mirror segments, and you can use those contacts, make them simultaneously using an anisotropic conductive film approach, a bonding approach. But for this to work, I need to be able to deposit a transistor for each one of those elements. And working with Professor Tom Jackson and the Electrical Engineering Department at Penn State, we were able to deposit zinc oxide thin film transistors. These are deposited by a plasma-enhanced atomic layer deposition approach to put down both the gate dielectric and the functional semiconductor, the zinc oxide. And then we aimed every technique that we knew how to use to figure out whether the zinc oxide affected the piezoelectric or the piezoelectric affected the zinc oxide. And the 2 processes appear to be totally separate, one from another. So you can now actually grow directly on your microelectromechanical system, so on your lead zirconate titanate coated substrate, an insulating layer. We use a benzocyclobutene, which is photopatternable. We then deposit the titanium gate metallization and pattern that. and then with plasma-enhanced atomic layer deposition, deposit the gate dielectric in the semiconductor, pattern those, and then lift off the titanium sources and drains, and then the entire thing is covered with a layer of alumina for protection. So this shows an example of a 5x5 array of piezoelectric actuators on a 400 micron thick piece of glass for the use in this X-ray telescope application. We actually built an electrostatic discharge protection circuit down here in the zinc oxide. And we sent this off to our collaborators. We were very proud. When they mounted it in their mounting rig, they actually broke a piece of the substrate. Alas, they broke it on the side opposite for where we had our electrostatic discharge protection circuit. And when you break something, you stress it. And we just took a material that converts between mechanical and electrical energies, and we stressed it. So we partially damaged the electronics as we did this. So I don't have a perfect set of data. But what you can see is as we progressively actuate 5 different elements on this device, you can actually move the deflection patterns. It's not perfect. You see a lot of coupling along the columns. That coupling is probably associated with damage of the aluminum oxide dielectric when we broke that device. And although you might never build an X-ray space telescope, this general approach to being able to integrate functional electronics on functionally active, electromechanically active devices will be very interesting for a wide variety of applications, including improved medical ultrasound transistors, array devices that will allow you, for example, to map the pressure distributions in a shoe, very useful for the aging population, whereas people age, their balance often degrades, and you can actually detect fall risks if you can put arrays of sensors in shoes. The last example of a microelectromechanical system that I'm going to walk you through is intended to begin to address the fact that Moore's law is progressively being challenged by the fact that we now make devices that are really, really thin. And although we've been able to make devices that are progressively laterally smaller, we have not been able to scale clock speed on devices since about 2003. And that choice to not scale clock speed is not because these faster transistors can't in fact, or the smaller transistors can't in fact run faster. The technology is capable of running faster, but it requires a lot more power to turn the devices, or in that case, because it's hard to turn the devices off if you actually run them at their limits. And so the fact that we choose to carry around devices that are powered by batteries is actually driving us in the opposite direction, where we're actually choosing to run computers slower in order to have long lifetimes. And that's a fundamental problem that's associated with the physics of the silicon switch. Turns on at 60 MeV per decade. If you want to get around that, you need to actually change the mechanism by which the transduction occurs. So you have to change the switch. And IBM came to me a number of years ago and said, we have a strange idea. We would like to take a piezoelectric material. Remember that piezoelectric materials elongate when you apply an electric field. And we want to use that elongation to compress a piezoresistor against a very stiff surround. And if you can do that using properties of known bulk materials, a piezoelectronic device actually allows you to have low energies and higher clock speeds. So the estimate is that we should be able to take clock speeds up an order of magnitude while simultaneously dropping powers by factors of 50 to 100. This would be very appealing for a number of applications, including wearable electronics, including being able, maybe perhaps getting away from having to build server stations by power plants, which is the current approach in order to be able to handle the power draw on some of those devices. So this is an extremely cool idea, and the question is, can you actually build that? And so our approach was to say, well, in this case, we need a piezoelectric that elongates as much as possible for the smallest possible applied voltage. So we need a large piezoelectric D33 coefficient. We use lead magnesium niobate lead titanate. Here's that strain compared to a material like lead zirconate titanate. You can see the slope is very much larger, so it's much more appealing for this application. For the piezoresistor, we use samarium selenide. Samarium selenide undergoes a insulator to metal phase change continuously as a function of pressure. The mechanism for that is shown here. This material has the rock salt crystal structure in which the samarium F levels lie about half an electron volt below an empty D band. And at low pressures, that half an electron volt is enough that the material operates as an insulator. Under compression, this F level moves closer to the empty D band so that I can actually thermalize carriers into that band without a phase transition, which means that it is not inherently hysteretic, as would be the case of a material like a metal insulator transition and vanadium oxide. It still takes sort of depressingly large values of pressure to get a 5-order of magnitude change in the electrical resistance, but it is possible. And so working with IBM Corporation, we actually built several generations of these devices, and they work. So we still haven't achieved the full levels of switching. We haven't achieved the speeds that you'd need to use to replace silicon, but it is interesting that these devices actually function as intended. So to try and begin to understand the key scaling issues in these materials, we have looked at, well, first off, we were working with IBM. They can't put anything smaller than an 8-inch wafer through their process line. I work at a university. I can't get an 8-inch wafer in through the gate valve in any of my vacuum deposition systems. And unfortunately, all lead-based materials, you pop the top on the vacuum chamber, and it takes like 10 runs in order to get the sputter rates consistent, and you have to pop the top for every wafer. So no dice. We actually developed a chemical solution deposition route to do this, which is not how you would do it in industry, but it allowed us to actually make prototype devices. And so then the key question is, if I take this device and I now laterally pattern it, there's sort of two things that could happen. The first thing is that, okay, we have now a very thin film on quite a thick substrate. Remember that this thin film is trying to elongate this way and contract laterally, and it has to pull the substrate along with it if it's a continuous film, which clamps the response. So if I subdivide the material, it should be less clamped and the response should get better. That would be sort of the ideal situation. The less ideal situation is these are all complex oxides. Start with 4 cations. If you mess up the stoichiometry or the crystallinity, the properties go to 0. And so I need to be able to take this complex chemistry and pattern it without degrading the crystallinity or the properties, because if I etch-induce damage, okay, we're never going to be able to do the scaling. And so we learned how to reactive ion etch devices. I show here ones that are about a micron in arm size. We've gone down to about 1/10 of a micron in arm size. And what we find is here's the measured data compared to what we would have predicted from a finite element model. We, in fact, can achieve relatively good improvements in the properties as we laterally scale the devices. To assess how we should be able to change the piezoelectric coefficient, we used finite element modeling. We looked both at a 70-degree sidewall angle and a 90-degree sidewall angle for pillar and strip structures. And what you see is that when you can drop between a width to thickness aspect ratio on the order of 1, you can get to properties that are good enough for this device actually to give you what you need to replace the silicon transistor. The finite element models say that you should laterally declamp about the outer half micron of the device. And so it doesn't matter how big you make that device, you're going to declamp the outer half micron. And so we then tried to make devices where we could characterize that. To do this, we made strips of various widths by a reactive ion etching process, went to the advanced photon source, where we could use an X-ray fluorescence detector. As we laterally move the piezoelectric element, we can detect where we are on that device via the fluorescence detector, and then we can use an X-ray beam to simultaneously measure the X-ray pattern, and we can do that as a function of voltage. So we can measure the piezoelectric coefficients of these films. We weren't able to measure our smallest devices because we literally didn't have a beam size that was small enough to do that. We were about 250 nanometers lateral resolution. But here are results on thicker, literally wider devices. And what you can see is that the values that we achieve sort of on the edges of any of those feature sizes are declamped. And then the average piezoelectric response begins to climb once you get below feature sizes of about 2 microns. If we estimate, so that's where we actually made our experimental results. We physically know how to grow features down to about this size, and so it looks like we actually can achieve the piezoelectric coefficient in real materials, even those made by chemical solution deposition, to actually run the piezoelectronic transistor. These data show comparisons of the X-ray measurements in blue with atomic force microscope measurements in red and the finite element model in black, and the 3 data sets overlay fairly nicely. So to conclude, hopefully what I've shown to you is that it is possible to utilize piezoelectric microelectromechanical systems for a number of applications. If you are able to control the domain state of that material, you can optimize materials for particular applications, and I showed you a particular example of that in the case of the energy harvesting. And there's, I think, a lot of room to continue to move forward by being able to integrate these functional electromechanically active materials with electronics for array devices, or perhaps actually as electronics if we totally replace silicon as the transistor. So with that, I will stop and take any questions that you have.